Okay, hello everyone. So here's a video covering all topic 4 questions in the 2019 papers, or the higher level papers. So first question here is from May 19, time zone 1. We have some microwaves that are being transmitted and they are incident on a pair of narrow slits. So we're going to be looking at double slit interference, two source interference here. And W is right in the middle, equidistant from the slits. We observe maximum intensity there. So, and then they explain how X and Y are also intensity maxima with one minimum between them. They're consecutive maxima. So you have to imagine sort of the intensity pattern goes something like this, our usual interference pattern, yeah? So why are intensity maxima observed at X and Y? So that's because we have constructive interference at those points, and they are going to arrive in phase, and the amplitudes add to give this maximum amplitude that gives maximum intensity. So the waves interfere constructively at X and Y. They arrive in phase. You know, at X we have a path difference that is equal to 1 wavelength. The path difference is lambda. At Y it is 2 lambda, etc. So they arrive in phase and the amplitudes add to give a maximum amplitude. Okay. Then we are given the distance S1 to Y, and the distance from S2 to Y is from slit 1 and slit 2. We're given the two distances, so we can easily work out the path difference. And we know Y is where we have a path difference that is equal to 2 wavelengths. So path difference equals 2. We subtract those two, 1.243 minus 1.181, 0.062 meters, and that is 2 lambda. So the lambda we get is 0.031 meters, and we then need to find the frequency. Easy enough, use the wave speed equation, because these microwaves are of course electromagnetic waves. They travel at the speed of light in air, which is roughly the same as the speed of light in empty space. So we just use 3 times 10 to the 8 meters per second, and then you get something like 9.7 gigahertz, 10 to the 9 hertz. Okay. Then why will the maxima observed at W, X, and Y have different intensities? Well, you know, in perfect two-source interference, where the screen is very far away from the slits and so on, we won't really notice a dip in intensity, but very often we do, because the single slit diffraction is often not negligible, so you get this diffraction envelope that modifies the intensity. You could also argue that X and Y are slightly further away from W, so and we know that the intensity of a wave sort of drops with distance to the source. So yeah, you can mention a couple of different reasons. I'm just going to say that X, Y are slightly further away, compared to then W. but we can also say, or the width of slits is not negligible. Typically it's not negligible. So a diffraction envelope modifies the intensity. This is, by the way, topic 9 in HL physics. So yeah, this HL question goes into topic 9 here a bit too. But then we're back to topic 4 now, that the microwaves emitted by the transmitter are horizontally polarized. Okay, and then the receiver has a filter. Initially it's receiving maximum intensity. Okay, but then it's rotated through 180 degrees, and we know, of course, that when the polarizers are crossed, when they're at a 90-degree angle to each other, then the intensity is going to drop to 0 because we block all the radiation with the polarizing filter. But then as we keep on turning, then again the receiving filter is going to let all the horizontally polarized light through, and this is a cosine squared function from Malus's law. So that's topic 4, polarization. Okay, then we have the November 19 topic 4 question. So here we have a traveling wave, and we're looking at the solid line first. Then 0.2 milliseconds later it moves a little bit, and we have to calculate the speed of this wave. Okay, so basically just have to look at, well, how far has it traveled in those 0.2 milliseconds. So we have to see that the wave has traveled. So if I look at one point on the wave, then it's moved to this point, like the crest has moved a certain distance. Now, how long has it moved? We need to take a good look at the units on the axis. So one little square, how wide is that? And a good way to do that is often I can see that 0.2 meters corresponds to 10 small squares. So I know that sort of the width of one little square is going to be 0.2 meters divided by 10. That's 0.02 meters. And I can see that the wave has traveled sort of 2.5 squares. So that's 0.05 meters that it's traveled in those 0.2 milliseconds, not meter seconds, milliseconds. And you plug that in and you get 250 meters per second. Then we have to calculate the frequency. Well, if we know the wave speed and if we can read off, which we can, the wavelength, then we can get the frequency. So the speed over wavelength. And what is the wavelength? Well, just look from crest to crest. That's easy to see. It's 0.3 meters. And we get something along the lines of 830 hertz. Then it's showing P and Q, the displacement of two particles in the medium, and this state and explain which particle has the larger magnitude of acceleration. So we know that the particles in the medium are undergoing simple harmonic motion, and we know that the further away the particle is from the equilibrium, the larger acceleration it has. So clearly Q has the larger acceleration. So Q has the larger acceleration because all particles are undergoing simple harmonic motion and acceleration proportional to negative the displacement, right? Largest amplitude when we have the largest displacement, and Q has largest displacement from equilibrium. P is actually at the equilibrium. Okay, so P has 0 acceleration. Then we now are making standing waves. When the frequency is 360 Hertz, we get the third harmonic. Okay, so make sure you can recognize this as the third harmonic. We've got like 3 antinodes closed at both ends, standing waves with nodes at both ends, 3 antinodes. Point X is a distance of 10 centimeters from the oscillator. So we can sort of, X is around here somewhere, right? Close to the oscillator. State the number of all the points on the string that have the same amplitude. So, well, same amplitude is going to be this point there, this point there, this point there. Now, there are also 2 points down here that have the same amplitude, but they are not going to be they won't have the same phase as X. They won't be oscillating in phase. They'll be completely out of phase. So we remove those, and we can see that we basically just have those other 3 points that are going, up and down with the same amplitude, and they are completely in phase with X. And frequency is reduced to 120, so that's a third of the frequency of the third harmonic. So we're just going to get the first harmonic, and the first harmonic is, of course, this. We have half a wavelength across the length of the string, and it looks like that. So yeah, that was it. All the sort of topic 4 2019 questions with a little bit of topic 9 mixed into one of them. There you go. Bye bye.